Hi, welcome to Parametric House. In this Grasshopper script, I want to show you how you can use the Galapagos component to optimize a rectangle inside any polyline or a curve. So let me explain the logic behind this. First, what we have here is a simple polyline or curve. We want to produce the rectangle inside it, and this is the rectangle it's going to produce, and it's going to optimize it using Galapagos. So let me explain what are the parameters here. The first one is an evaluate curve. So obviously we just want to start with a point on the curve. So here you can see here that I can change the location anywhere on the polyline or a curve. Then we have a projection of projecting this point on the polyline by rotating the direction and rotating the x direction here in the z direction. So actually it's going to rotate it around the z, and it's going to project it all around the polyline. You can see that there are some of them it doesn't have any answer, but anyway, this is going to give us the second point. After producing the second point, we can see this line as the first line of the rectangle. What I have used here is the rectangle 3-point command. You can find it in curve primitive, and here you can see that rectangle 3-point. Create a rectangle from 3 points, which is the edges, and 1 point on the other side. So for the first two, obviously we're going to use this point and the projection. To find the third point, it's really important that it has to sit on the polyline or the curve. We can't make it like the also the last point sit on the polyline, because it's not going to be a rectangle, and obviously we're going to lose lots of results. So what I have done here is made a line, as we explained here, and then we have a perpendicular frame. We have the perpendicular frame and use the y direction to again project the point. This is going to be the projections. So obviously this is going to also project on here. The reason we are projecting here is to make like 3 points. One is from this perpendicular frame, one from this point, and another one from this point. Okay, so assume that we have 3 points, and obviously the smallest point or the shortest point is going to be the length of the rectangle or the width of the rectangle. Okay, so as you can see here, when I change this perpendicular frame, it's going to play around and it's going to find if there is any location smaller than this length or the line. So let me show you here. Maybe we have, okay, I think this is a good example. So when we have produced that line here, right, we have a projection from this point here on the polyline, we have a projection from this point on the polyline, and we have also a projection from this point on the polyline. So assume that we have these three. We're going to find the smallest one, and that is going to, so that was the first edge. That is going to produce the third edge, which is going to make the rectangle anyway. So here you can see that I have made 3 projections, find the distances, and then sort it from smallest to biggest. And then when you sort this, you also going to sort these 3 points that we have the projection, and obviously we're going to pick up the first one, which is the smallest one, and that is going to go to the third point on the opposite side. As you can see here, it says point along rectangle opposite to AB, which was this one. Okay, now that we have the rectangle, we have to do some tests here. The area is going to be the goal we want to maximize, but first let's check if this is intersecting. For example, if I also, let me explain this side problem. If I make this point here, there are 2 solutions. One is going to be in this direction, and if I flip it, another one is going to go in the second direction. So I have made a switch, which is going to also help the Galapagos to actually explore anything possible here. Okay, so that is the switch here. Let's go back to the area. So when we have the area, we're going to dismiss those that have intersections. So for example, this one, as you can see here, has intersections, is going outside the boundary. So here we're going to find the trim width region component. You can find it from intersection, trim width region. And what we have done here is we have trimmed this with the boundary, which was this one, the polyline. And here you can see that we have some curves outside the boundary, which is going to be these two anyway, or whatever it is. We can just count them. So obviously, to don't have any curves outside the boundary, we have to find a zero number. We tested, is it equal to 0? It says true or false, which this one is false. And if we give it a number, false is going to be 0. So let me type it here. False is equal to 0, true is equal to 1. And if we multiply that with the area, the 0 multiplied by the area is going to be 0, which is going to actually bring the area down, and it's going to be good for us because we want to find the maximum. And if it's true, we're going to multiply with that area, which is going to be the area, and that's okay. So this is a simple test we can do, and then we can give the Galapagos to all the sliders. As you can see here, we can control the location of the point, the rotation, also we can give this with, I'm going to use the shift key to give it to the perimeter, and also the switching. Okay. And now the goal is to find the maximum area. So I'm going to just double click here, click on maximize, because we want to, this is going to be the first run of the simulation. So the initial boost is really important because I've made this to 10 because it's going to make 500 results at the first stage. 500, whatever you produce at the first stage is going to get better results because it's going to give the chances to find a good solution. And then after that, it's going to be 50-50. Each step is going to take 50 steps. So I'm going to increase that initial boost to 10. The population 50 is okay. The goal is to maximize solver and put this to see all the results. So I'm going to just click here and start the solver. And as you can see here, it's going to just play around with all of these sliders. It's going to test if it's intersecting or not. And obviously we want to maximize this number to the maximize area we can. So as you can see here, it's trying to maximize. We can give it some chances. The first step is like 500, and the undefined is that it doesn't have any area because it's like intersecting or maybe whatever. And for the first step, it found 34,000. So as you can see here, the other steps is like 50 from minimum to maximum, and then we just have reached, if we stop it here, you can see this is the maximum result it's getting. As you can see here, if I reinstate, this is also so if I go to the first step and reinstate this one, this is like 34,000. This is the biggest number. I guess that it doesn't have any way to produce that number in the other parts of the steps, so you can rely on the first step, like this is the maximum one you can get. But for this one, it's 31,000, so it's a little bit smaller, but anyway, this is like the best solution we can get, and you can use the Galapagos to find the best results. And if we want to, we can give this to any curve. Maybe we just want to define a curve and find the biggest rectangle on this. So I'm going to run it for maximize, and again you can see it's running. So whenever you want to find the best solution, you can stop at the first step, which is, for this one, it's like 56,000, and then it's trying to reach the 56,000 at the first step. So yes, and it broke it. So the ranking here is like 57,000. It's going up 63,000. This is really important because if you can just change this, maintain in breeding, this is going to help to find breakthroughs towards the solution. So here you can see it's even reaching more numbers, 70,000. So that's great. It's going up. And here, if we stop at 71,000, I think it's even going up more. But anyway, let's stop it here and say I wanted to see this one. So if I reinstate it, this is the biggest rectangle possible. You can see it's like near this curve. Maybe you can just adjust it a little bit to get the final results. And this was for the first step it found. Then it just optimized it here. I think this is like one of the big breakthroughs we have here, because we have 56,000, then we break it at here 57,000. That was a new solution. Then it just tried to produce new results. It jumped to 68,000, 70,000. Just make this a little bit bigger, 71,000, and that is like the biggest number we can reach. I wanted to show you this second example that you can see you can produce that. So anyway, I just wanted to give you this Grasshopper script. You can use it to find the biggest rectangle, maybe in an area you want to calculate. If you have any other solutions or maybe ideas, you can just comment down this lesson. We can recreate it with Grasshopper anyway. And what do you think about this tool? Is it useful? If you have any idea, just comment below. And thanks for watching. See you next time. Bye.